corresponding to 0.7054. I will first look to the left, it's 0.5. And then if I look up, it is 0.54. That's how I find the Z value. Okay, I'm going to show you how to find it using the calculator. So let me use the calculator to find that the Z value corresponding to 0.0982 is Z is less than 1.33. So I'm going to get a calculator right now. We want to confirm that Z is less than 1.33 corresponds to 90th 0.9082. That's the same as 91st percentile. 91st percentile. Okay, so I'll turn my calculator on. All right, and I go to second distribution, inverse norm, the inverse of what you're doing. Remember, we have been using normal distribution, normal CDF, but now anytime I'm given area inside the normal curve, and I'm told to find the Z value, I'll do inverse norm. Okay, so inverse norm, which is number 3, and then area under the normal curve that I'm told to find is 0.9082. The mean of a standard normal is 0, standard deviation is 1, and I'm going to calculate. Therefore, if I approximate this to 2 decimal places, I have that the 91st percentile is the same as 1.33, approximately. So if I approximate this to 2 decimal places, my answer is 1.33. So anytime you are told to find the Z value corresponding to a number given to you inside the normal curve, of course, that number has to be less than 1. It cannot be up to 1. It cannot be more than 1. Okay. Let's get another example. So let's use this worksheet that we put in. I put this worksheet in some time ago. Let's do it again. Use it. Anytime I am given area inside the normal curve, and I'm told to find the Z value. For example, if I'm given area to the left, like in number 7, so what I'm going to do is inverse norm, because they already gave me area. So they're asking me to find the Z value corresponding to that area. Find the Z score indicated by the graph. So they gave me the area, they drew the graph for me, they shaded the region. So, and this number 0.2776 is actually less than 0.5. That means that the Z value I'm going to get will be a negative, because the Z value is less than 0.5. So I can just use my calculator or use the chart. So I'm going to use my calculator first. So I'm going to clear, then second distribution, inverse norm, number 3, put that number in my calculator, 0.2776, 0.2776. All right, the mean of a normal distribution is 0, standard deviation is 1, and I'm going to calculate. When I hit enter, then it means that the Z value corresponding to 0.2776 inside the normal curve, it's negative 0.59 approximately. Remember, this is area given to you. Therefore, the value you just found is the Z score. So the Z score, and I hope you know it is negative. It's okay to be negative, because 0.27 is less than 0.5. So it has to be negative though. Okay. What if I am told to find the area to the right? If I'm told to find the area to the right, what I'm going to do is find this, do 1 minus 0.8205, and then find this. So what I'm going to do is 1 minus, because the total area inside the normal curve is 1. So I will find the area to the left. And how do I do it? Do 1 minus. Okay, what is the z value corresponding to the boundary line? I'm going to get my calculator. I can do it with my calculator. I don't have to, but anyway. So I do second distribution, number 3. And then right here, instead of putting in the number 0.8508, I'll just put in 1 minus 0.8508. Why? 0.8508. All right, I'm going to put 808. Okay, and everything is good. So I'm going to hit enter, enter, enter. And then I hit enter. And I'm going to get an answer. And the z value corresponding to that number is negative 1.03, maybe negative 1.04. Why? Why is it negative? Because the boundary line is on the left-hand side of the mean. The boundary line is on the left-hand side of the mean. Therefore, the z value corresponding to that is negative 1.04. Okay, so just want to make sure that we know how to find percentile. So let me do one more example here and then. So these are called percentiles. Percentile. So suppose I'm told to find P83 like this. P83. Find P83. It means 83rd percentile. By the way, let me draw it. If I'm told to find P83, I'm going to shed it in a normal curve. Okay, 83% or 83rd percentile, that's what it means. So this area inside the normal curve is 83.83. So if I'm told to find the area to the left, and that's what it means, P83, find the 83rd percentile. P20, find 20th percentile. Even this one where this is still the same thing as P.8, P80. This is P35 and so on. Okay, so they are percentiles. So this is how to find percentile using your calculator. Find the 83rd percentile. Another way of telling you that. Okay, so you get your calculator. You the inverse num. Why? Because you're going to find z. Inverse num. I mean, you're going to second distribution, number 3. So you get inverse num. And now I am going to put in 0.83, 0.83, and that is 83rd percentile. The mean is 0, standard deviation is 1. I am going to calculate. Therefore, the 83rd percentile is something as 95.17%. Okay, the z-score corresponding to 83rd percentile is 0.9542%. 0.9542, no percent. So it shouldn't be there. All right, so let's go to practice test. I want you to know that practice test is already in Blackboard and it is assigned in practice test is already in Blackboard and it's assigned in my lab maths. Our test will be after spring break. Next week will be spring break. Next week will be our spring break. Okay. So I am going to get a practice test. The practice test is already assigned. Question number 1 is the same thing as what we have been doing. This says find the z-score such that the area under the standard normal is 0.89. Same thing we have been doing. Okay, so what I'm going to do now is, if you're told to draw a picture, it's always good to draw a normal curve. So draw a normal curve, and 0.89 is greater than 0.5, so it's on the right-hand side. So 0.89 is this region, area to the left of a normal curve, 0.89. And the question is, find the z-value corresponding to this boundary line. That's what it's asking us. It's also called percentile. So what is the 89th percentile? That's another way of asking you about percentile. You can use your calculator or you can use the chart. We are going to use both the chart and the calculator. So you do inverse norm, area to the left in decimal, that's the percentile. The mean is 0, standard deviation is 1. And then you put it in your calculator. So let's put it in our calculator now. I'm going to clear everything. Second distribution. Inverse norm is number 3. And the percentile is 0.89 or 89th percentile. But I have to put it in decimal, 0.89. The mean of a standard normal is 0. Standard deviation of a standard normal is 1. Okay, so why are you not moving? Oh, it's not moving. Okay. Okay, what I'm going to do is paste, enter, because everything is, oh, my calculator is okay, 0. And then arrow down, enter. Therefore, the z-score corresponding to the 89th percentile is 1.227. The z-score corresponding to 89th percentile is 1.227. So that is 1.227. Z-score corresponding. So whenever you're given area inside the normal curve, you could be told to find the z-score. And whenever you're told to do that, you're going to use inverse norm. Okay. Okay, so let's look for another one. You could also be given the area. We already talked about that, but it doesn't harm to say it again. If I could be given the area inside the number, like these ones here, and that z-score corresponding to the boundary line, given a percentile, told to find the z-score corresponding to the boundary line. Okay, so I am told that the area on each end, let's look at this number 8 here. Area on each end is 0.1251, 0.1251. And I'm told to find z-score to the left and z-score to the right. Because they already told me that the area under the normal curve, they are equal on the tails. I know that normal curve is symmetrical. So the normal curve is symmetrical. The area under the normal curve on the right is 0.1251. The area to the right is 0.1251. I just need to find one z-score, area to the left. Let me do that. And when I get that area, I will switch it around. Okay, so second inverse norm, second distribution, number 3. Okay, and the area to the left is 0.1251. So 0.1251, and The mean of a standard normal is 0, standard deviation is 1. So I am going to paste, and it's asking me, is that what you want? Yes. I'm looking for the 12.5 percentile and the Z value corresponding to that. Okay, so the Z value corresponding to the 12 percentile on the left is negative 1.15, negative 1.15. All right, so negative 1.15 on the left-hand side, and it is 1.15 on the right-hand side. Why? Because the normal curve is symmetrical. If the area on the left is equal to the area on the right, then the normal curve is symmetrical, so the Z value only differ by sign. So you can say, so Z alpha over 2, I'm going to explain that later on, is plus or minus 1.52. Why? Plus or minus 1.52, because there are two tails. We call them two tails. If I am given area to the right and I'm told to find the boundary line, all I have to do is 1 minus that area to the right, because the total area in that normal curve is 1. So 1 minus 0.1093. I can go ahead and type it in the way it is in my calculator. So I can just type it in like that. Number 3. So 1 minus that area to the right given to me. So I'm subtracting minus 0.1093, 1093. So what I'm going to get is, all right, so what are all those things there? All right, 1 minus 0.1093. When I arrow down, I get past, and I'm going to, so now I found the Z value. Note that that is Z value, that's not area. So the Z value corresponding to 0.1093 area is 0.2683. That's Z value. Why is it positive? Because the point is at the right-hand side of the mean. Why is it positive? Because the point is at the right-hand side of the mean. Okay, I think enough of this. So let's go to section 8.3, 8.1. So the first thing we're doing in 8.1 is looking at the, let's look at the notes. 8.1. Let's look at the notes for 8.1 right here. That's not what I'm looking for. Okay. Okay, so that's what I'm looking for. I got it here. All right, so on 1, remember, test number 3. And the test contains 6.1, 6.2, 7.1, 7.2, and 8.1. 8.1 is called the central limit theorem, even though maybe a book may not call it central limit theorem. But you'll be hearing central limit theorem everywhere if you log into YouTube. So make sure you understand that central limit theorem and the sampling distribution of the means are the same. Sampling distribution of the means and central limit theorem. Okay, so there are 2 important questions we should know how to answer before we finish 8.1 next class. We're finishing the next class, but we're starting it today. Describe the distribution of the sample mean normal population. What does it mean? Whenever it's normal population, it means that sample size must be greater than 30. The standard deviation of the population must be known. That's normal population. And the sample must be from a simple random sample. It has to be from a simple random sample, a non-biased sample. If a data comes from a non-normal population, so in this one, by the way, we use the z-value, z-score. All right, when it is a normal population. When it's a non-normal population, we know that sample size may actually be less than 30, and population standard deviation is unknown. And actually, sample may be from a normal population too. Sample may be from a normal population. Okay, so, and whenever this happens, we are going to be using what is called a t-distribution. In a non-normal population, we use t-distribution. In other words, when the sample size is unknown, when the sample size is less than 30 and the population standard deviation is unknown, it's a question for t-distribution. Question for t-distribution. So in this unit, we shall learn the properties of normal distribution, which you already know from unit 1, and the properties of t-distribution. We shall be applying t-distribution in solving problems in this unit. Okay, so this is the learning objectives for today. We are going to be looking at normal population and non-normal population. What does it actually mean when we are told to find the mean distribution or the distribution of means? What does it mean? I'm going to quickly pull down here. I am going to get a picture, a better picture for this central limit theorem. And then I'm going to draw my own picture. So what in the world does it mean when we say the sampling distribution of the mean? That's the picture I'm talking about here. So the first picture is that if I have a sample of 200, I could be given a sample of 200, and I can be given a sample size of, maybe, it doesn't matter, maybe the sample size is something, but I make 200 samples out of it. If I make 200 samples out of it, and then find the mean of each small sample. Find the mean of each small sample. So these are the means of those 200 small samples. The central limit theorem says that the distribution of this mean, in other words, if I draw a histogram, it's a crooked, but anyway, if I draw a histogram of this distribution, that the histogram will be normally distributed. I will have one peak. If I draw a histogram, it will have one peak, and the mean of this histogram, the mean, okay, the mean of the central limit theorem will be equal to the mean of the original data. I want you to know the difference. This is the mean of central limit theorem when x bar is on top of it. This is the mean of the original data. X bar is not on top. This is the random variable x. Mean here is the mean of the original data. The central limit theorem also says that the standard deviation of the original data is standard deviation, But the standard deviation of the mean distribution, sigma x bar, is equal to the standard deviation of the original data divided by square root of sample size. Okay, so in summary, let me just make sure I summarize what the central limit theorem says. So central limit theorem says it doesn't matter if the original data is skewed right, normally distributed, or skewed left. Let me call this one A, skewed right. Let me call this one B. Let me call this one C. The central limit theorem says it doesn't matter if the original data is A, B, or C. A is skewed right. B is skewed, well, it's not skewed, it's bell-shaped. And C is skewed left. The distribution of means must be approximately normal. I want you to see me draw X bars here. The distribution of means. This distribution was meant of sample means. The mean of the distribution of means is called mu X bar. It has to be equal to the mean of the original data. The standard deviation of the central limit theorem, distribution of means, is equal to standard error, and standard error is the same as standard deviation over square root of sample size. Okay, so standard error, the standard deviation of central limit theorem is called standard error. Okay, so what we're going to do now is, this is just the theory, the definition. I just explained the definition. So this is just what I just said. Let's go to a practice test and see a question like this. We'll answer the simple questions now so that next class, this is 8.1 by the way. So this is 8.1. And by the way, let's make sure we conclude. So the original data has z-score of z equal to value minus mean over standard deviation. But the central limit theorem, z central limit theorem, is equal to x bar. The value is x bar because the distribution is made of means. Value x bar minus mu x minus mean divided by the standard error. So this is the standard deviation of central limit theorem. Okay. All right, so we are going to go to our practice test and look at some questions on. Okay, so let's get up to our practice test. And we are going to answer questions on central limit theorem. We already answered number 1, which is on percentile. I'm only looking for questions on central limit theorem. I hope you know we have answered this question. We answered this question number 5 last week in binomial distribution. I hope you studied binomial distribution. All right, so the next one now is 8.1. That's what we're doing now. Okay, so I am looking for a question that is on central limit theorem. So we can see how a question will look. How does a question on central limit theorem look? As an example here. Okay, it's not coming out. All right, got it? Okay, so we are given number 8 right here, and we are told to find, given those numbers, and we are told to find the mean of the central limit theorem. So we are given some information. The first information given to us is that the mean of the original data is 65. The standard deviation of the original data is 15. The sample size of the original data is 23. All right, okay, so we see the sample size is less than 30. So when you start doing central limit theorem, when you start doing confidence interval in unit 4, you know that this is a data, a number for t-distribution because sample size is less than 30. It's a non-normal distribution. Okay, but anyway, let's continue with that. Anyway, so now they're asking us to find the mu x bar, and this mu x bar is find the mean of the central limit theorem, or the mean of the mean distribution. The mean of the mean distribution is equal to the mean of the original data according to the definition of central limit theorem. The mean of the mean distribution is equal to the mean of the original data. And then we're also told to find the standard error. The standard error is the same as standard deviation of the original data divided by square root of sample size. Okay, so I can calculate this because everything is given to me. The standard deviation is given to me to be 15. The sample size is 23, so I divide 15 by square root of 23. And then I get my calculator and put them in. So I'm going to clear the screen, and I'm told to find the standard error. So 15 divided by square root of 23. What am I looking for? I'm looking for the standard error. And what is standard error? Standard error is the standard deviation of the central limit theorem, of the distribution of means. The standard error is the standard deviation of the distribution of means. So I end up having 3.123. That is the standard error. That is the standard error. And notice that the standard error, which is 3.123, notice that the standard error is smaller than the standard deviation, smaller. We can ask ourselves why. Why is the standard deviation bigger than the standard error? So the standard error must always be smaller than the standard deviation of the original data. And I'm going to say it again. The standard error must be smaller than the standard deviation of the original data. Why? Because I'm always going to be dividing by square root of sample size. Sample size could be 3, could be 4. So I'm dividing the standard deviation by a large number. So that's why my answer is smaller. So that is why the standard error is always smaller than the standard deviation of the mean of means. Okay, so I have answered question number 8, and that is a question in 8.1. That is a question in 8.1. That is a question in 8.1. All right, I want you to note, let me make sure that I write this down. I'm going to write that because, yeah, I want to differentiate between the standard deviation of an ordinary normal distribution and the standard deviation of the standard deviation of a mean distribution is written as sigma x bar. It is not the same as standard deviation. No, they are not the same. In this particular time, the x bar is the random variable. X bar is a random variable.